What if everything you know about geography is based on lies? The facts you've carried around for years are often misunderstood. Using the latest 2025 data and research, I've compiled 50 geography myths that even smart people still believe. Some of these facts are taught in schools right now, others are spread by documentaries, and a few are so convincing that geography experts believe them for decades. The truth is going to completely change how you see our world. Let's start with something that thousands of people risk their lives for every single year. World's tallest mountain. Mount Everest draws hundreds of climbers each spring, with adventurers paying tens of thousands of dollars and risking their lives in the death zone above 26,000 feet. But here's the thing that's going to blow your mind. They're not actually climbing the tallest mountain on Earth. The real giant is Mauna Kea, a dormant volcano sitting in Hawaii. When you measure from its true base to its summit, Mauna Kea stretches an incredible 33,474 feet into the sky. That makes Everest's 29,032 feet look pretty ordinary by comparison. We're talking about a mountain that's more than 4,400 feet taller than the supposed king of peaks. The reason nobody talks about this is simple. Most of Mauna Kea hides underwater. The volcano rises from the ocean floor, with only 13,796 feet visible above sea level. New 2025 oceanographic surveys using advanced sonar mapping have confirmed these underwater measurements with unprecedented accuracy. So while thousands of climbers continue risking everything to reach Everest's summit, they're actually scaling a mountain that doesn't even hold the height record. But if Everest isn't the tallest mountain, surely it must at least reach closer to outer space than any other peak on our planet. Earth's closest point to space. Wrong again. Since Everest stands taller than any other mountain above sea level, logic tells us it must reach closest to outer space. After all, height equals proximity to the cosmos, right? Well, our planet has other plans. Earth isn't the perfect sphere you see in textbook diagrams. Our planet's radius measures about 6,378 kilometers at the equator compared to 6,357 kilometers at the poles. The physics behind this involves Earth's rotation creating centrifugal force that pushes mass outward at the equator. So which mountain actually extends as the farthest point from Earth's center? The answer takes us to Ecuador, where Mount Chimborazo rises from the Andes. This ancient volcano doesn't come close to Everest's elevation above sea level, reaching only 20,564 feet compared to Everest's 29,032 feet. But here's where geography gets interesting. Because Earth bulges at the equator, Chimborazo's summit extends further from the center than Everest's, even though it is lower above sea level. The latest 2025 satellite measurements using GPS and laser altimetry show that Chimborazo's peak extends 6,384 feet further from Earth's center than Everest's summit. Your location on the planet matters more than your altitude when you're trying to reach for the stars. Speaking of location, let's talk about how badly we misunderstand where entire continents actually sit on our planet. Africa's hemispheric location. Picture Africa on a world map. Where do you see the equator cutting through the continent? Most people imagine it slicing somewhere near the top, making Africa primarily a southern hemisphere landmass. This mental image shapes how we think about African weather, seasons, and agriculture. Close your eyes and try to visualize exactly where that equatorial line crosses Africa. Got your mental picture ready? Now prepare to have it completely flipped upside down. The 2025 Continental analysis reveals that almost two-thirds of Africa actually sits north of the equator. That means the majority of this massive continent experiences northern hemisphere seasons, weather patterns, and agricultural cycles. Consider Cairo, Egypt with its 20 million residents living firmly in the northern hemisphere. Even Nigeria's Lagos, home to 15 million people, lies above the equatorial line. This geographical reality explains why northern African countries have different seasonal patterns and climate zones than many people expect. This misconception about Africa's hemispheric position leads people to misunderstand the continent's climate diversity, agricultural potential, and seasonal patterns across 54 different nations. The truth is that our mental maps of entire continents can be completely wrong, and these mistakes extend far beyond just landmasses. Sometimes we get confused about the very names of countries themselves. Britain's political geography. Walk up to someone on the street and ask them what country the Union Jack represents. 9 times out of 10, they'll confidently answer, Great Britain. This mix-up happens so often that even news anchors get it wrong on international television. The Union Jack actually represents the United Kingdom, not Great Britain. These aren't just different names for the same place. They describe completely different things. The UK is a sovereign state of 4 nations, but Great Britain is only the main island. Great Britain is simply the name of the largest island in the British Isles. This island contains England, Scotland, and Wales, but leaves out Northern Ireland entirely. So when you say Great Britain, you're talking about geography, not politics. The United Kingdom includes that same island plus Northern Ireland, making it the complete political entity. This confusion creates real problems in international settings. Getting this terminology wrong in diplomatic situations can actually offend people from Northern Ireland, who might feel excluded when someone uses Great Britain to describe their country. Geographic misconceptions don't stop with political boundaries. Some of the most famous landmarks on Earth come with their own set of persistent myths that have fooled people for generations. The Great Wall's space visibility. Here's one of the most persistent myths in geography. You can see the Great Wall of China from the moon. This claim has survived for nearly a century, appearing first in a 1932 Ripley's Believe It or Not cartoon. That's right. This myth existed decades before humans ever left Earth's atmosphere. What do astronauts actually report seeing when they orbit our planet? The answer might surprise you. Crew members from the International Space Station consistently state that the Great Wall is nearly impossible to spot with the naked eye. The 2025 photographic evidence from the ISS confirms what space travelers have been saying for years. The wall simply blends into the surrounding landscape. The technical reasons are straightforward. The Great Wall was built using earth, stone, and brick materials that match the natural colors of the terrain. From space, these construction materials create no visual contrast with the surrounding environment. The wall's width, typically around 15 to 25 feet, is far too narrow to register as a distinct feature from orbital altitude. Meanwhile, modern highways with their dark asphalt surfaces and large airports with concrete runways show up clearly in space photography. These structures create sharp contrasts against natural landscapes, making them far more visible than China's ancient wall. But space isn't the only place where our eyes can deceive us about size and scale. Greenland's deceptive size. Look at any world map hanging in a classroom, and Greenland dominates the top portion like a massive green continent. The island appears so enormous that many people assume it rivals Africa in size. This visual impression has fooled geography students for generations. But how big is Greenland compared to other landmasses you actually know? The answer reveals one of cartography's most deceptive tricks. The Mercator projection, created in 1569 for ship navigation, accurately shows shapes and directions, but completely warps the size of anything near the poles. Updated 2025 analysis of projection distortions shows just how dramatic this warping becomes. The Mercator system stretches areas at higher latitudes, making northern regions appear vastly larger than they actually are. This mathematical distortion affects how millions of students perceive global geography. Greenland's true area measures 836,330 square miles. That makes it smaller than the Democratic Republic of Congo, which spans 905,355 square miles. When you see these landmasses displayed using accurate equal-area projections, Greenland shrinks dramatically while Congo maintains its actual size. Side-by-side comparisons using modern mapping software reveal the shocking difference. What appears as a continent-sized landmass on classroom maps is actually just the world's largest island. These projection distortions extend beyond individual countries to affect how we understand entire continents themselves. Australia's continental status. Ask anyone to name the smallest continent, and they'll confidently say Australia. This seems obvious when you look at traditional maps showing Australia as a lonely landmass surrounded by ocean. But what actually defines a continent in the first place? The answer isn't as simple as measuring land area. Continental definitions involve complex geological structures, tectonic plates, and continental shelves that extend far beyond visible shorelines. The traditional seven-continent model taught in schools is largely a cultural construct, not a scientific classification based purely on geological criteria. Here's the shocking truth from 2025 landmass measurements. Europe is actually smaller than Australia. Europe measures approximately 10.18 million square kilometers, while Australia spans 7.69 million square kilometers. The confusion comes from how we define continental boundaries, which often follow cultural and political lines rather than geological ones. But the real eye-opener involves Australia-Oceania as a complete continental system. This broader definition includes New Zealand, Papua New Guinea, and thousands of Pacific islands scattered across millions of square kilometers of ocean. The continental shelf connecting these landmasses creates a massive geological unit that dwarfs most other continents. When geologists examine tectonic plates and continental crust, Australia-Oceania becomes a giant that simply appears small on surface maps. Our misconceptions about size don't stop with continents. Sometimes the most famous examples of entire geographical categories aren't what they seem. The world's largest desert. The Sahara Desert holds the crown as the world's most famous desert. When people picture endless sand dunes and scorching heat, they're imagining the Sahara's 3.6 million square miles stretching across North Africa. This massive expanse has shaped our understanding of what deserts look like for generations. But what actually makes a desert a desert? Most people assume it's about temperature and sand, but the scientific definition focuses on something completely different: precipitation levels. A desert is any region that receives less than 10 inches of rainfall per year. Temperature doesn't matter at all. This definition completely changes the desert rankings. Antarctica claims the title as Earth's largest desert at 5.4 million square miles. The entire continent receives almost no precipitation, making it technically more desert-like than the Sahara. The 2025 climate data shows Antarctica averages just 0.4 inches of precipitation over a 30-year period. That's less moisture than the driest parts of the Sahara receive. The continent's extreme dryness comes from its incredibly cold air, which can't hold much water vapor. Our mental image of hot, sandy wastelands as the ultimate desert environment completely misses the bigger picture of what deserts actually are. These misconceptions about scale and classification extend to other massive geographical features that span incredible distances. Russia's time zone count. Russia's massive territory spans 11 time zones, making it the country with the most time zones in the world. This impressive number gets repeated in geography textbooks and trivia contests around the globe. But here's what most people don't know. This number has actually changed multiple times over the past few decades. The Russian government has been tweaking its time zone system like a giant clock puzzle. In 2010, they reduced the zones from 11 to 9. Then in 2014, they expanded back to 11 zones where it stands today in 2025. These weren't random changes. Each adjustment aimed to solve real administrative headaches. The current 2025 time zone configuration creates a system where when it's noon in Moscow, it's already 10 p.m. in Vladivostok. This massive time spread creates serious coordination problems for the federal government. Scheduling meetings between regional officials becomes a logistical nightmare. Transportation systems struggle to maintain unified schedules across regions that are literally half a day apart. The economic impact hits businesses especially hard. Companies operating across multiple Russian regions must navigate communication windows that shrink dramatically due to time differences. Russia has essentially been running a real-time experiment in time zone efficiency. These geographical challenges of managing vast territories create interesting questions about how we represent distant places on maps. Alaska's geographic connection. Alaska appears on most U.S. maps tucked away in a corner box, completely separated from the other 48 states. This visual presentation makes Alaska look like a distant island floating somewhere in the Pacific Ocean. The separated placement creates a mental image that Alaska exists in geographic isolation from the rest of America. But is Alaska actually an island cut off from the continental United States? The answer reveals how map design can completely mislead our understanding of geography. Alaska maintains a direct land connection to the continental United States through Canada. The state shares an extensive border with British Columbia and Yukon Territory, creating an unbroken land bridge between Alaska and the lower 48 states. The 2025 geographic data shows Alaska's continental shelf extends far beyond its visible coastline, connecting directly to the North American continental shelf system. These underwater connections demonstrate that Alaska sits firmly on the same continental mass as the rest of the United States. The Aleutian Islands stretch across the Bering Sea, with some islands crossing the 180th meridian into the Eastern Hemisphere. Map representations consistently create misconceptions about Alaska's isolation by visually separating it from the continental United States for space-saving purposes. Alaska remains very much part of the North American continent, connected, both above and below sea level. But maps aren't the only place where our measurements of massive geographical features can be surprisingly unreliable. The world's longest river. For over a century, the Nile River has held the title as the world's longest river at 4,132 miles. Geography textbooks, encyclopedias, and countless documentaries have repeated this fact without question. But measuring a river's true length turns out to be far more complicated than simply drawing a line from source to mouth. The challenge starts with defining where a river actually begins. Rivers don't emerge from a single spring like a garden hose. They form from countless tributaries, seasonal streams, and underground sources that merge across vast watersheds. Determining which tiny stream counts as the true source becomes a judgment call that can add or subtract hundreds of miles. Advanced 2025 satellite mapping technology and high-resolution surveying techniques have revolutionized how geographers track river courses. These tools reveal subtle meanders and variations that earlier measurements missed entirely. The new data has sparked intense debates between supporters of the Nile and Amazon river systems. The Amazon's length calculations vary wildly depending on which tributaries you include and where you place the source. Different measurement criteria yield results ranging from 3,976 to 4,345 miles. Some calculations put the Amazon ahead of the Nile, while others maintain the Nile's lead. These measurement complexities extend beyond rivers to challenge our assumptions about places we consider completely uninhabited. Antarctica's human population. Antarctica stands as the ultimate symbol of isolation, a frozen wasteland where no human life exists. This image of complete desolation gets reinforced by documentaries showing endless ice sheets and brutal weather conditions. The continent appears too hostile for any permanent human settlement. But scattered across this supposedly empty landscape sit dozens of research stations humming with activity year-round. These facilities house sophisticated laboratories, communication equipment, and living quarters designed to withstand the harshest conditions on Earth. The 2025 data reveals thousands of people actually live in Antarctica throughout the year. These populations include scientists studying climate change, engineers maintaining critical infrastructure, medical personnel, cooks, mechanics, and communications specialists. The McMurdo station alone can house over 1,200 people during peak summer months, while smaller stations maintain crews of 20 to 50 people even during the brutal winter darkness. The key distinction lies between permanent residents and rotating researchers. Permanent residents commit to extended stays of a year or more, maintaining the stations and conducting long-term studies. Rotating researchers arrive for shorter periods, typically a few months, focusing on specific experiments or seasonal work. Climate change is actually driving increased human presence in Antarctica as scientists rush to document rapidly changing ice conditions. But speaking of extreme elevations, our planet holds surprises at the opposite end of the altitude spectrum as well. Earth's lowest point. The Dead Sea holds the famous title as Earth's lowest point on land, sitting at 1,412 feet below sea level. This massive salt lake attracts millions of tourists who come to float effortlessly in its mineral-rich waters. But is this really the lowest accessible point our planet has to offer? The question becomes more complex when you consider what counts as Earth's true lowest point. The 2025 elevation measurements reveal several contenders that challenge the Dead Sea's status. Advanced satellite-based systems and sonar mapping have dramatically improved measurement accuracy, giving us precise data about previously inaccessible locations. The Mariana Trench's Challenger deep plunges over 36,000 feet below sea level, making it the actual lowest point on Earth's surface. The Atacama Trench off Chile's coast reaches depths exceeding 26,000 feet. These underwater locations dwarf the Dead Sea's depression by enormous margins. Even among land-based low points, the Dead Sea faces competition from other geological depressions around the world. Ongoing tectonic activity constantly shifts these measurements. The Dead Sea itself continues dropping due to evaporation and water extraction, while oceanic trenches change through plate movements and seismic activity. Modern surveying technology shows that Earth's lowest points represent constantly shifting targets rather than fixed geographical features. But sometimes our misconceptions about places come from something as simple as their names. Iceland's climate reality. Iceland's name literally translates to Iceland, creating expectations of a frozen wasteland covered in glaciers and snow. This misleading label has convinced generations of people that Iceland sits buried under permanent ice sheets like its neighbor Greenland. The name suggests a harsh, uninhabitable Arctic environment where nothing grows. What does Iceland's landscape actually look like throughout the year? The 2025 climate data reveals average temperatures that rarely drop below freezing in coastal areas. Winter temperatures hover around 32 degrees Fahrenheit, while summers reach comfortable highs of 57 degrees Fahrenheit. These moderate conditions support surprisingly diverse vegetation, including grasslands, low shrubs, and forested areas that create genuinely green landscapes. Iceland's agricultural sector thrives despite its northern location. Farmers successfully raise livestock and cultivate crops like hay and potatoes across the island. Geothermal energy powers greenhouse operations that produce fruits and vegetables year-round, contributing to the country's food security and agricultural diversity. The Gulf Stream carries warm ocean currents directly past Iceland's shores, moderating air temperatures and preventing the harsh conditions expected at such high latitudes. This warm current creates milder winters and longer growing seasons compared to other Nordic countries at similar latitudes. Iceland turns out to be significantly greener than its icy name suggests. But geographic names can mislead us in other ways, especially when it comes to major waterways and their connections. The Panama Canal's ocean connection. The Panama Canal connects the Atlantic and Pacific Oceans, right? This seems like the most basic fact about one of the world's most important waterways. Every geography textbook shows the canal as a direct bridge between two massive ocean systems. But the technical definition of ocean boundaries tells a completely different story. The International Hydrographic Organization defines oceans, seas, bays, and gulfs with precise criteria that most people never consider. The 2025 oceanographic data reveals that ships entering the Panama Canal don't actually travel directly from ocean to ocean. Instead, vessels navigate through the Gulf of Panama on the Pacific side and the Gulf of Limon on the Atlantic side before reaching open ocean waters. This distinction creates real consequences for maritime law and navigation regulations. Ships transiting the canal face different legal frameworks depending on which specific water body they occupy at any moment. Environmental protection rules, pollution controls, and navigational safety requirements change based on whether vessels travel through gulfs, bays, or open ocean waters. The canal's route through artificial lakes like Gatun Lake adds another layer of complexity to maritime jurisdiction. International shipping regulations must account for these geographical technicalities when determining which laws apply to vessels at different points along the transit route. These precise definitions matter more than most people realize, especially when it comes to how we divide up the world's landmasses. The Europe-Asia continental divide. Continental boundaries reveal some of geography's most arbitrary decisions. Look at any world map and you'll see Europe and Asia labeled as separate continents. This division seems so obvious that questioning it feels ridiculous. The Ural Mountains create what appears to be a natural boundary between these two massive landmasses, reinforcing the idea that they represent distinct continental regions. But where exactly does Europe end and Asia begin? Try tracing that boundary line with your finger. The supposedly clear division becomes surprisingly fuzzy when you examine the details. Different countries actually define the Europe-Asia boundary in completely different ways, with some placing it at the Ural Mountains, others at the Caspian Sea, and still others following various river systems. The 2025 geological evidence reveals something that challenges everything we think we know about continental divisions. Europe and Asia sit on a single, continuous landmass with no geological separation whatsoever. The rock formations, tectonic plates, and continental crust flow seamlessly from Portugal to Siberia without any natural break. This division exists purely for cultural and political reasons, not geological ones. The boundary reflects historical power dynamics, cultural differences, and political conveniences rather than any physical reality. What we call Europe and Asia is actually Eurasia, one enormous continent that humans have arbitrarily split in half through centuries of convention. These artificial divisions shape how we visualize other remote regions of our planet. Arctic composition. The Arctic appears in most people's minds as a vast sheet of floating ice stretching endlessly toward the horizon. This image dominates documentaries and textbooks, showing a featureless white expanse where nothing exists except frozen water. The Arctic seems like Earth's most barren region, devoid of any substantial geography beneath the ice. What actually lies hidden under all that frozen surface? The answer reveals one of geography's most underestimated regions. The 2025 Arctic research using advanced satellite mapping and bathymetric surveys shows massive landmasses scattered throughout what appears to be empty ice fields. The Canadian Arctic archipelago alone contains over 36,000 islands, many larger than entire countries. These substantial land formations include mountain ranges, valleys, and continental shelves extending hundreds of miles underwater. The Lomonosov Ridge runs directly under the North Pole like a massive underwater mountain chain. Greenland's continental shelf stretches far beyond its visible coastline, creating underwater territories larger than most European nations. Climate change is acting like a geographic reveal tool, exposing landforms that remained hidden for millennia. Melting ice sheets uncover islands, rocky outcrops, and coastal formations that completely change Arctic maps. What we thought was simple ice turns out to be a complex network of islands, underwater mountains, and continental extensions. But our misconceptions about extreme environments don't stop with cold regions. Desert temperature variations. When you hear the word desert, your mind immediately conjures images of scorching sand dunes and blazing heat waves. The Sahara Desert has shaped this universal picture with its endless golden landscapes and temperatures that can melt car tires. This hot, sandy wasteland represents what most people consider the ultimate desert environment. But what about deserts where snow falls regularly and temperatures plummet below freezing? These cold desert environments exist across the globe, challenging everything we think we know about desert climates. The 2025 data on cold deserts reveals some shocking statistics. The Gobi Desert, stretching across Mongolia and China, experiences winter temperatures as low as -40 degrees Fahrenheit. Snow covers the landscape for months, creating scenes that look nothing like traditional desert imagery. The Patagonian Desert in Argentina regularly sees freezing temperatures and receives occasional snowfall throughout the year. Some deserts experience sub-zero conditions more often than tropical heat. These frozen landscapes receive less than 10 inches of precipitation annually, which is the actual scientific definition of a desert. Temperature has nothing to do with desert classification. Only moisture levels matter. Pictures of snow-covered sand dunes and ice-crusted desert rocks completely shatter our expectations of what deserts look like. But if temperature doesn't define desert environments, hottest locations, what determines where Earth the equator runs around its most extreme heat, like a giant belt, sitting at 0 degrees latitude? Most people assume this must be where our planet reaches its hottest temperatures. After all, the equator receives the most direct sunlight year-round, so logic tells us it should be a scorching hot zone. But the actual temperature records tell a completely different story. The 2025 global temperature data reveals that some of the highest recorded temperatures occur in desert regions thousands of miles away from the equatorial line. The Sahara Desert holds multiple heat records despite sitting well north of the equator across northern Africa. These extreme temperatures happen because of factors that have nothing to do with latitude. Desert regions lack cloud cover, allowing intense solar radiation to reach the ground unfiltered. Sand absorbs this radiation and releases it as heat throughout the day. Low humidity means there's no moisture in the air to moderate these temperature spikes. Altitude also plays a major role in temperature variations. Higher elevations experience cooler temperatures because thinner air can't trap heat effectively. Meanwhile, low-altitude desert valleys concentrate heat near the surface, creating furnace-like conditions. Geographical features like mountains and valleys create microclimates that completely override latitude-based temperature predictions. These same principles apply to how we misunderstand where different animal species actually live around the globe. Global penguin distribution. Penguins waddle across your imagination surrounded by Antarctic ice sheets and endless white landscapes. This image gets reinforced by documentaries showing emperor penguins huddling together against brutal polar winds. The association between penguins and Antarctica seems so natural that most people assume these birds exist nowhere else on Earth. But penguins actually live in places where you'd never expect to find them. The 2025 penguin population data reveals thriving colonies scattered across multiple continents in surprisingly warm locations. Over 150,000 African penguins live along the coasts of South Africa and Namibia, where temperatures regularly exceed 80 degrees Fahrenheit. These birds swim in waters warmed by the Atlantic Ocean, building nests on beaches that tourists visit for sunbathing. South America hosts several penguin species along its coastlines, including massive colonies in Argentina and Chile. Australia's southern shores support tens of thousands of little penguins that come ashore nightly in temperate coastal towns. The Galapagos penguin lives directly on the equator, making it the only penguin species found in the northern hemisphere. Different penguin species developed specialized adaptations for their specific climates, from heat-dispersing behaviors to varied feather densities. Most penguin species actually inhabit temperate regions rather than polar environments. But animal distribution isn't the only area where popular environmental claims need closer examination. Amazon oxygen production. The Amazon rainforest produces 20% of Earth's oxygen. This claim appears in environmental campaigns, school textbooks, and nature documentaries around the world. It's become the go-to statistic for explaining why we need to protect the rainforest. But what if this widely accepted fact is completely wrong? The real story about Earth's oxygen production happens in a place most people never consider. The 2025 atmospheric studies using advanced gas spectrometry and satellite monitoring reveal that ocean phytoplankton generate the majority of our planet's oxygen. These microscopic organisms floating in seawater perform photosynthesis on a massive scale across billions of square miles of ocean surface. The Amazon's oxygen contribution gets dramatically overstated because people ignore a crucial detail. The rainforest consumes oxygen too. Every plant and animal in the Amazon breathes, using oxygen for cellular respiration. Decomposing leaves, fallen trees, and dead organisms consume enormous amounts of oxygen as bacteria break them down. This consumption largely cancels out the oxygen production from photosynthesis. The Amazon's net oxygen contribution to our atmosphere is essentially zero. Meanwhile, ocean phytoplankton pump out oxygen without the massive consumption that happens in dense forest ecosystems. Ocean health matters far more for oxygen production than rainforest preservation. But environmental misconceptions aren't limited to present-day processes. Sometimes we completely misunderstand the timing of massive geological changes happening right beneath our feet. Ongoing continental drift. Continental drift continues reshaping our planet at this very moment. Most people think continental drift happened millions of years ago when dinosaurs roamed the Earth. This geological process seems like ancient history, something that shaped our planet's layout long before humans existed. The idea of continents slowly drifting across the globe feels like a relic from Earth's distant past. But continental drift never actually stopped. The 2025 GPS measurements reveal something that completely changes how we understand our planet's behavior. Advanced satellite positioning systems can now track continental movement with incredible precision, measuring shifts down to the millimeter. The data shows that continents continue moving several centimeters every single year. North America drifts away from Europe at roughly 2.5 centimeters annually. Australia moves northward at about 7 centimeters per year, making it one of the fastest moving continents. These measurements accumulate over time, creating substantial geographical changes within human lifespans. This ongoing movement creates real problems for GPS systems, which must constantly update their reference points to maintain accuracy. Earthquake prediction models rely heavily on tracking these continental shifts to identify areas of increasing tectonic stress. The continuous motion of tectonic plates directly influences where and when major earthquakes will occur. These same forces that move entire continents also affect smaller bodies of water in ways that might surprise you. Mediterranean Sea changes. The Mediterranean Sea appears as permanent as the Alps or the Sahara Desert. This ancient body of water has hosted civilizations for thousands of years, from Greek traders to Roman emperors. Its stable coastlines and familiar shape create an impression of geological permanence that seems unshakable. But what does the latest geological evidence reveal about the Mediterranean's future? The 2025 tectonic data shows something that completely challenges our assumptions about this sea's stability. Advanced seismic monitoring and plate movement measurements reveal the African and Eurasian tectonic plates are actively converging beneath the Mediterranean basin. The Mediterranean Sea is actually shrinking due to these massive tectonic forces. The African plate pushes northward at measurable rates, gradually squeezing the Mediterranean basin smaller. This convergence happens unevenly across the region, with some areas experiencing faster closure than others. The timeline for this geological process spans millions of years, but the changes are already measurable. Increased seismic activity and volcanic eruptions throughout the region reflect this ongoing tectonic pressure. Coastal areas will experience significant alterations as the basin continues contracting. Climate patterns, marine ecosystems, and regional geography will all transform as this ancient sea gradually closes. But sometimes geographical features disappear from our view in much more immediate ways. New Zealand map representation. World maps routinely exclude entire countries from their representations, creating gaps in our global understanding. New Zealand gets left off world maps so often that the country created an entire tourism campaign called Get New Zealand on the Map. This wasn't just a clever marketing stunt. It addressed a real problem that happens with shocking regularity across atlases, textbooks, and official publications worldwide. How frequently does this geographic oversight actually occur? The 2025 cartographic analysis reveals that New Zealand appears on only 67% of world maps published in educational materials. That means 1 out of every 3 maps simply ignores a country with 5 million people and 2 major islands larger than many European nations. The omission rate jumps even higher for digital maps and infographics used in news media, where space constraints and simplified designs regularly eliminate New Zealand entirely. Weather maps, political graphics, and economic charts consistently show Australia floating alone in the South Pacific, as if New Zealand vanished completely. These omissions create serious consequences beyond hurt feelings. Tourism boards report measurable drops in visitor inquiries when New Zealand disappears from travel maps. International businesses struggle with logistics planning when shipping maps exclude major ports like Auckland and Wellington. The pattern reflects deeper biases in cartographic representation, where mapmakers prioritize Northern Hemisphere regions and larger landmasses while treating smaller nations as expendable details. But sometimes the places we think exist as solid ground turn out to be far more unstable than we imagine. North Pole geography. The North Pole presents a completely different geographical reality than most people imagine. Both poles sit at Earth's extremes, so they should be similar, right? This mental image places the North Pole on stable land where explorers can plant flags and build permanent structures. But what actually exists at exactly 90 degrees north latitude? The reality completely shatters this assumption. The North Pole sits on nothing but shifting sea ice floating over incredibly deep ocean water. There's no land whatsoever beneath that famous geographical point. The 2025 Arctic ice data reveals ocean depths exceeding 13,000 feet directly under the North Pole. Advanced sonar measurements show this massive body of water constantly moving due to ocean currents and wind patterns. The ice itself drifts several miles each day, meaning the North Pole location changes continuously. This creates a stark contrast with Antarctica's South Pole, which sits on solid continental bedrock thousands of feet thick. While the South Pole supports permanent research stations built on stable ground, the North Pole offers nothing but temporary ice that could crack or drift away at any moment. The North Pole turns out to be far more ephemeral than most people realize, existing as a shifting point on an ever-changing ocean surface rather than a fixed geographical landmark. But geographical misconceptions extend beyond natural features to include the very definitions of political boundaries themselves. World's smallest country. Country recognition involves complex criteria that go far beyond simple land measurements. Vatican City holds the official title as the world's smallest country at just 0.17 square miles. This tiny nation sits entirely within Rome, Italy, housing approximately 501 residents as of 2025. But what about other micronations that claim independence around the world? The question becomes surprisingly complex when you examine what actually makes a country legitimate. Several self-declared microstates exist globally, from the Principality of Sealand on an offshore platform to the Republic of Molossia in Nevada. These entities claim sovereignty but lack international recognition. The 2025 data on country recognition reveals the strict criteria nations must meet. A legitimate country needs defined territory, permanent population, functioning government, and most importantly, the capacity to engage in diplomatic relations with other states. Vatican City checks all these boxes through its unique status as the Holy See's seat. Vatican City maintains its sovereignty through the 1929 Lateran Treaty, which established its independence through international agreement. The nation conducts diplomacy with 183 countries and holds observer status at the United Nations. Its global influence stems from representing 1.3 billion Catholics worldwide. Country size measurement involves far more than square footage. Political recognition, diplomatic capacity, and international standing determine true sovereignty more than physical dimensions. These same political considerations shape other seemingly straightforward geographical features in unexpected ways. International date line geography. The international date line creates one of geography's most politically influenced boundaries. Picture this line as running precisely along the 180th meridian from pole to pole. This seems like the most logical way to divide Earth into different calendar days. After all, why would an imaginary line marking time zones need to zigzag across the Pacific Ocean? The actual path of the international date line reveals a line that curves, bends, and deviates dramatically from the 180th meridian throughout its journey across the Pacific. The 2025 mapping data shows these aren't minor adjustments. The line makes massive detours to accommodate island nations and territories. The line curves around Alaska's Aleutian Islands to keep the entire state on the same date as the continental United States. It makes another major deviation around Kiribati, where the government requested in 1995 that all their islands share the same calendar day. Similar adjustments accommodate other Pacific nations like Tonga and Samoa. These deviations create serious complications for international travel and business scheduling. Travelers crossing the line must adjust their calendars by a full day, but the irregular path makes it difficult to predict exactly where these time jumps occur. Political convenience trumps geographical logic in determining where tomorrow begins. But geographical naming conventions create confusion in other ways too, especially when different regions use completely different terms for identical phenomena. Hurricane versus typhoon classification. Most people assume hurricanes and typhoons are completely different types of storms. The names alone suggest distinct weather phenomena with unique characteristics and formation processes. News reports reinforce this perception by treating Atlantic hurricanes and Pacific typhoons as separate categories of natural disasters. But what do meteorological definitions actually reveal about these massive storm systems? The 2025 classification data shows something that challenges this widespread assumption. The World Meteorological Organization uses identical criteria to define both hurricanes and typhoons, focusing on sustained wind speeds, low pressure centers, and formation over warm ocean waters. These storms are exactly the same meteorological phenomenon occurring in different geographical locations. Hurricanes develop in the Atlantic Ocean and Northeast Pacific, while typhoons form in the Northwest Pacific. The Saffir-Simpson hurricane wind scale measures intensity identically regardless of location, with Category 1 through Category 5 classifications based purely on wind speed measurements. Regional naming conventions create this confusion entirely through linguistic tradition rather than scientific distinction. Different meteorological agencies adopted separate terminology for ease of local communication and coordination. The underlying physics, formation processes, and destructive capabilities remain identical whether you call them hurricanes or typhoons. Storm classification depends more on geography than meteorology, making location the only real difference between these powerful weather systems. But speaking of mysterious locations, some places on our planet remain far more hidden from human exploration than most people realize. Mariana Trench exploration. The Mariana Trench represents Earth's final frontier right here on our own planet. Most people assume this deepest part of our ocean sits largely unexplored, like an alien world waiting for discovery. After all, we've sent more people to space than to the bottom of the Mariana Trench. But what has actually happened with deep-sea exploration in recent years? The 2025 expedition data reveals something that completely changes this perception. Advanced remotely operated vehicles and autonomous underwater systems have conducted dozens of successful missions to the trench's deepest regions. These sophisticated machines can withstand pressures exceeding 1,000 times greater than at sea level. High-resolution bathymetric mapping has created detailed three-dimensional models of the trench's complex topography. Scientists have discovered hydrothermal vents, unique geological formations, and thriving ecosystems of specialized organisms that survive in complete darkness. New sensor technologies capture unprecedented footage of creatures living in conditions once thought impossible for life. International collaborations bring together researchers from multiple countries, sharing resources and expertise to tackle these extreme exploration challenges. Modern materials engineering enables equipment to operate at depths exceeding 36,000 feet below sea level. Deep ocean exploration advances rapidly through technological innovation, but some natural phenomena on our planet's surface follow patterns that completely contradict popular wisdom. Lightning strike patterns. Lightning never strikes the same place twice. This old saying gets repeated so often that most people accept it as scientific fact. The phrase suggests that lightning somehow remembers where it hit before and actively avoids those locations. But what happens when you actually examine real lightning strike data? The 2025 meteorological data reveals a completely different story. Advanced lightning detection networks track millions of strikes annually, creating detailed maps of where lightning hits most frequently. These systems use electromagnetic sensors and satellite monitoring to record precise strike locations with unprecedented accuracy. Some places get hammered by lightning repeatedly throughout the year. The Empire State Building takes an average of 25 lightning strikes annually. Radio towers, cell phone antennas, and skyscrapers experience multiple strikes during single storms. Mountain peaks in regions like Colorado and Montana get struck dozens of times each summer. Geographical features create natural lightning magnets that attract strikes predictably. Elevated terrain provides the shortest path between storm clouds and ground. Metallic structures conduct electricity efficiently, making them prime targets. Areas with high humidity and frequent thunderstorms generate the atmospheric conditions necessary for repeated lightning activity. Certain locations experience lightning strikes so frequently that meteorologists can predict seasonal patterns with remarkable accuracy. But predictable patterns aren't limited to weather phenomena. They extend to how we measure and understand our planet's most essential resources. Great Lakes water volume. The Great Lakes contain 20% of the world's fresh water. This statistic appears in environmental reports, geography textbooks, and conservation campaigns across North America. It's become the standard measurement for explaining the region's water importance. But what happens when you examine the actual global freshwater distribution using current data? The 2025 hydrological studies reveal a more complex picture of worldwide water resources. Advanced satellite monitoring and ground-based measurement systems provide unprecedented accuracy in tracking global freshwater volumes. These comprehensive surveys include glacial ice, groundwater aquifers, rivers, lakes, and atmospheric moisture across all continents. The Great Lakes actually hold closer to 6% of the world's surface freshwater, not 20%. This lower percentage reflects better measurement techniques and recognition of previously uncounted freshwater sources. Massive aquifer systems beneath Africa and South America contain far more water than earlier estimates suggested. Antarctic ice sheets hold approximately 68% of global freshwater, while Greenland contains another 24%. These revised figures dramatically affect water security planning for both regional and global communities. The Great Lakes remain critically important for the 40 million people who depend on them, but understanding accurate distribution helps prioritize conservation efforts worldwide. Geographic misconceptions don't just affect how we understand water resources. They also shape our assumptions about where the world's most dramatic weather events actually occur. Global tornado distribution. Tornado activity spans the globe in ways that challenge common assumptions about where these destructive storms actually form. Ask most people where tornadoes occur, and they'll immediately say the American Midwest. This makes perfect sense given how much media coverage focuses on Tornado Alley, stretching from Texas to Nebraska. The United States reports over 1,200 tornadoes annually, creating the impression that these rotating storms are uniquely American phenomena. But what happens when you examine tornado activity across the entire globe? The 2025 meteorological data reveals tornado occurrences on every continent except Antarctica. These statistics show significant tornado activity in regions most people never associate with severe weather. Argentina experiences hundreds of tornadoes each year across its expansive plains. The Pampas region provides the same flat terrain and atmospheric conditions that make the American Great Plains so tornado-prone. Bangladesh reports dozens of deadly tornadoes annually, with some causing more casualties than American storms due to higher population density. Canada documents several hundred tornadoes each year, particularly in Ontario and the Prairie provinces. Australia's southeastern regions see regular tornado activity during their storm season. Even the United Kingdom experiences around 50 tornadoes annually, though most remain relatively weak. The geographical factors that create tornadoes, flat terrain, moisture availability, and colliding air masses, exist worldwide. These same geological forces that shape tornado patterns also create much larger structural features across our planet. Ring of Fire structure. The Pacific Ocean's geological boundaries reveal complexity that defies simple explanations. Most people picture the Ring of Fire as a single, massive fault line circling the Pacific Ocean like a giant crack in Earth's surface. This image gets reinforced by simplified diagrams showing one continuous line of geological activity stretching from Alaska to Chile. The name itself suggests a unified feature rather than something more complex. But the actual geological structure looks far more intricate when you examine it closely. The 2025 tectonic data reveals something that completely challenges the simple fault line concept. Advanced seismic monitoring and plate boundary mapping show the Ring of Fire consists of multiple overlapping tectonic plates, subduction zones, transform faults, and spreading centers all interacting simultaneously. The Pacific Plate alone interacts with the Philippine Sea Plate, Eurasian Plate, North American Plate, and several smaller plates through different geological processes. Some areas experience subduction where oceanic plates slide beneath continental plates. Other regions feature transform faults where plates slide horizontally past each other. Spreading centers create new oceanic crust while convergent boundaries generate intense pressure and heat. These diverse tectonic processes operate independently, yet interconnect to create the Ring of Fire's volcanic and seismic activity. The Ring of Fire functions more like a complex network of geological systems rather than a single continuous feature. But geological forces don't just destroy landscapes through earthquakes and eruptions. Desertification, reversal. They also create and restore entire landscapes through deliberate human intervention. Desertification seems like a one-way street toward environmental disaster. Once fertile lands turn to barren wasteland, most people assume the damage is permanent. Sand dunes advance, vegetation dies, and communities abandon their homes forever. This narrative suggests that deserted landscapes represent irreversible ecological collapse. But what happens when scientists and engineers actively fight back against advancing deserts? The 2025 data on land restoration projects reveals something remarkable happening across multiple continents. Advanced water harvesting systems, drought-resistant crop varieties, and innovative irrigation technologies are actually reversing desertification in regions once considered hopeless. The Great Green Wall initiative stretches across Africa's Sahel region, creating a massive barrier of trees and vegetation against the expanding Sahara Desert. This project has already restored millions of acres using strategic reforestation and sustainable agriculture techniques. Meanwhile, China's Kabuki Desert Project transformed vast desert expanses into thriving ecosystems through sand stabilization and groundwater recharge methods. Modern drip irrigation systems deliver water directly to plant roots while minimizing evaporation losses. Rainwater harvesting techniques capture precious moisture during brief precipitation events. Specially bred drought-resistant crops survive harsh conditions while gradually improving soil health through their root systems. These projects prove that environmental changes, once considered permanent, can be completely reversed through targeted intervention. But not all environmental variations happen uniformly. Sea level measurements reveal striking regional differences that challenge widespread assumptions. Most people assume that sea levels rise uniformly across the globe, like water filling a bathtub. Climate change reports often present global averages that suggest every coastline faces identical threats. This creates the impression that Miami and Mumbai experience the same rate of sea level increase. But regional variations in sea level change tell a completely different story. The 2025 oceanographic data reveals dramatic differences in how sea levels behave around the world. Some coastal regions experience sea level rise 3 times faster than the global average, while others actually see water levels decline. The east coast of the United States faces accelerated sea level rise due to weakening Gulf Stream currents that normally push water away from shore. Meanwhile, parts of Scandinavia experience falling sea levels because land masses continue rising after glacial ice melted thousands of years ago. Alaska's coastline drops in some areas due to tectonic uplift, while other sections flood from thermal expansion. Gravitational effects from melting ice sheets create another layer of complexity. When Greenland's ice melts, its reduced gravitational pull allows water to flow toward distant coastlines rather than staying nearby. Ocean currents redistribute this water unevenly across different regions. These regional variations extend beyond ocean levels to affect atmospheric conditions in equally surprising ways. Global ozone distribution. Atmospheric chemistry reveals patterns that contradict popular assumptions about ozone protection. Most people picture the ozone hole as Antarctica's problem, a seasonal gap that opens over the South Pole each spring. This creates the impression that ozone depletion only affects polar regions, while the rest of the world remains protected by a healthy ozone layer. But ozone measurements from around the entire planet tell a different story. The 2025 atmospheric data reveals something that challenges this localized view completely. Advanced satellite monitoring and ground-based stations track ozone levels across all latitudes, showing significant variations that extend far beyond Antarctic boundaries. The tropics actually maintain lower ozone concentrations year-round compared to mid-latitude regions. Meanwhile, the Arctic experiences its own seasonal ozone depletion, though less severe than Antarctica's famous hole. Even temperate zones show fluctuating ozone levels that affect UV radiation exposure for billions of people. The Brewer-Dobson circulation transports ozone from equatorial regions toward the poles through massive atmospheric currents. This global transport system means ozone depletion in one region affects atmospheric chemistry worldwide. Increased UV radiation from reduced ozone creates health risks, including higher skin cancer rates, cataracts, and ecosystem damage across multiple continents. Ozone depletion represents a global atmospheric issue with worldwide implications, rather than an isolated Antarctic phenomenon. But atmospheric misconceptions aren't the only environmental assumptions that need challenging when it comes to understanding life in extreme conditions. Cold water coral reefs. Coral reefs exist in environments that completely contradict our tropical paradise assumptions. Picture coral reefs, and you immediately see crystal clear turquoise waters and colorful fish swimming through vibrant coral formations. These warm, shallow ecosystems exist in places like the Great Barrier Reef and Caribbean waters where sunlight penetrates easily. But thriving coral reefs actually exist in places you'd never expect to find them. The 2025 marine biology data reveals extensive coral reef systems flourishing in the frigid depths of oceans worldwide. These cold water coral discoveries completely challenge everything we thought we knew about where reefs can survive. Advanced deep-sea exploration technology has uncovered massive reef structures off the coasts of Norway, Ireland, and throughout the North Atlantic and Mediterranean Sea. Cold water corals like Lophelia pertusa build complex, three-dimensional structures without any sunlight whatsoever. These organisms survive through filter feeding, capturing nutrients directly from the surrounding water rather than relying on symbiotic algae like their tropical cousins. The reefs support diverse marine communities including specialized fish species, crustaceans, and invertebrates adapted to extreme cold and darkness. These deep-sea reefs thrive in water temperatures near freezing, often at depths exceeding 1,000 feet where no light reaches. But marine ecosystems aren't the only natural resources that defy our expectations about availability and distribution. Groundwater depletion. Hidden beneath our feet lies a water crisis that most people never consider. Most people assume groundwater exists as an endless underground ocean waiting to be tapped whenever we need it. This perception treats aquifers like massive underground lakes that refill themselves automatically. Farmers drill wells expecting unlimited water for irrigation, while cities expand their water systems assuming groundwater will always meet growing demand. But what happens when you examine the actual data on global aquifer health? The 2025 hydrological studies reveal something alarming. Advanced satellite measurements from GRACE-FO missions and sophisticated monitoring systems show groundwater levels dropping at unprecedented rates worldwide. These measurements track changes in Earth's gravitational field caused by shifting underground water masses. The Ogallala Aquifer beneath America's Great Plains has lost enough water to drain Lake Erie. China's North China Plain faces critical depletion, threatening food production for hundreds of millions of people. California's Central Valley has sunk over 28 feet in some areas due to groundwater extraction. Land subsidence damages buildings and infrastructure as underground spaces collapse. Saltwater intrusion contaminates freshwater supplies along coastlines. Wetlands disappear as water tables drop below critical levels. These changes force entire agricultural regions to abandon farming or switch to less water-intensive crops. Communities migrate from water-stressed areas toward regions with reliable supplies. But geological processes don't just affect what lies beneath the surface. Island formation processes. They also shape the very formation of new landmasses across our oceans. Most people picture islands as mountain peaks that happen to stick up above ocean water. This simple explanation gets taught in elementary schools and seems logical enough. Mountains exist on land, some must extend underwater, and the tallest parts create islands. The 2025 geological data reveals island formation involves far more complex processes than just underwater mountains. Advanced satellite imagery and deep-sea surveys show islands arise through completely different mechanisms that have nothing to do with mountain peaks. Coral atolls like those in the Maldives form when tiny organisms build massive reef structures over thousands of years. These coral polyps create ring-shaped islands around submerged volcanic craters, with a central lagoon marking where the original volcano once stood. The delicate balance between coral growth rates and rising sea levels determines whether these islands survive or disappear entirely. Continental shelf islands off Florida's coast form through sediment accumulation rather than volcanic activity. Rivers deposit materials that build up over time on shallow continental shelves. Meanwhile, volcanic islands like Hawaii emerge from underwater lava eruptions that cool and solidify into new landmasses. Sea level changes dramatically affect all island types, exposing new land during low periods while submerging existing islands when waters rise. These geological forces operate on massive scales, but they're not the only planetary systems that follow patterns more complex than most people realize. Jet stream variability. High-altitude air currents reveal complexity that defies meteorological expectations. Most people assume jet streams follow predictable pathways across the globe, like invisible highways in the sky that rarely change course. Weather forecasters have relied on these steady patterns for decades, expecting the high-altitude air currents to behave consistently from season to season. This assumption forms the foundation of long-term weather prediction models used worldwide. But what happens when these supposedly stable atmospheric rivers start behaving erratically? The 2025 meteorological data reveals something alarming about jet stream behavior. Advanced atmospheric monitoring systems show the jet stream developing increasingly large loops and meanders that persist for weeks instead of days. These amplified waves create what scientists call blocking patterns, where weather systems get stuck in place. The Arctic warming at twice the global average has weakened the temperature gradient that normally keeps jet streams steady. This reduced contrast between polar and mid-latitude regions allows the jet stream to develop massive swings that carry warm air unusually far north while dragging cold air masses deep into southern regions. These persistent patterns trap weather systems in specific locations, creating prolonged heat waves in some areas while other regions experience unseasonable cold snaps. The jet stream changes are actively reshaping regional climates, making extreme weather events more frequent and intense than traditional climate models predicted. But atmospheric systems aren't the only natural phenomena that move in ways that contradict popular assumptions. Glacier movement rates. Glaciers demonstrate movement patterns that defy expectations about ice behavior. Most people picture glaciers as massive ice sheets that barely creep forward over centuries. This slow-motion image dominates nature documentaries, showing ancient ice formations that seem frozen in time. The assumption makes sense. After all, we're talking about enormous blocks of ice weighing millions of tons. But actual glacier velocities using modern measurement techniques reveal movement speeds that completely shatter this sluggish stereotype. The 2025 glaciological data shows some glaciers racing forward at incredible rates that would shock most people. Advanced GPS monitoring and satellite tracking capture these surprising dynamics with unprecedented precision. The Greenland ice sheet contains glaciers flowing over 10 kilometers per year. That's roughly 27 meters every single day. Some glaciers experience surge events where their speed increases by factors of 10 or even 100 within weeks. These surging glaciers can advance several meters daily, reshaping entire valleys and creating significant flooding risks. Multiple factors influence these surprising velocities. Warmer temperatures create meltwater that lubricates the glacier's base, allowing massive ice masses to slide more easily across bedrock. Underground water systems act like conveyor belts, dramatically accelerating ice movement. Slope angles and internal glacier structure also affect flow rates in ways scientists are still discovering. These dynamic ice movements represent just one example of how Earth's fundamental systems behave far differently than most people expect. Earth's magnetic field changes. Earth's magnetic field operates as another constantly changing system that defies common assumptions about planetary stability. Most people assume our planet's magnetic field remains perfectly stable, providing reliable compass directions that never change. This seems logical since navigation has depended on magnetic north for centuries. Sailors, pilots, and hikers all trust their compasses to point in the same direction year after year. But recent magnetic measurements from around the globe tell a different story. The 2025 geomagnetic data reveals something that challenges this fundamental assumption. Advanced monitoring stations worldwide show Earth's magnetic field experiencing continuous fluctuations in both strength and direction across different regions. The magnetic North Pole has been racing toward Siberia at accelerated speeds, moving faster than scientists previously recorded. This rapid movement requires constant recalibration of navigation systems used by airlines, shipping companies, and military operations. GPS technology faces interference from ionospheric disturbances caused by these magnetic field changes. The relationship between magnetic north and true north constantly shifts as the poles move. Maps and geographic databases need frequent updates to maintain accuracy. Compass users must account for changing magnetic declination values that vary by location and time. Even satellite navigation systems experience errors during periods of increased magnetic activity. These magnetic disruptions affect far more than just navigation tools. They influence atmospheric conditions and geological processes in ways that extend throughout our planet's interconnected systems. Volcanic eruption types. These same forces that constantly reshape our planet also create the dramatic volcanic events that capture global attention. Most people picture volcanoes as massive mountains that spew red-hot lava down their slopes. This classic image dominates movies and documentaries, showing molten rock flowing like rivers of fire. But this simple lava-only view completely misrepresents how volcanoes actually behave. The 2025 volcanological data reveals volcanic eruptions involve far more complex processes than just lava flows. Advanced monitoring systems now classify eruptions based on explosivity, gas content, and environmental interactions. These classifications show that many eruptions never produce visible lava flows at all. Plinian eruptions like Mount St. Helens in 1980 violently eject gas, ash, and pyroclastic material instead of gentle lava streams. These explosive events create fast-moving currents of hot gas and volcanic debris that obliterate everything in their path. Meanwhile, phreatomagmatic eruptions occur when magma interacts with water, producing some of the most unpredictable and dangerous explosions on Earth. Volcanic gas emissions, including sulfur dioxide and carbon dioxide, create significant geographical impacts through acid rain and climate effects. These invisible releases often cause more widespread damage than visible lava flows. Ash clouds travel thousands of miles, disrupting air travel and affecting air quality across entire continents. Volcanic geography involves far more complexity than simple lava flows suggest, but atmospheric systems themselves operate through processes equally misunderstood. Atmospheric water cycle. Water movement through our atmosphere follows patterns that challenge everything taught in basic science classes. Science textbooks teach the water cycle as a perfectly contained system where water simply moves between Earth's oceans, atmosphere, and land surfaces. This closed-loop model shows evaporation, condensation, and precipitation happening endlessly within our planet's boundaries. Nothing enters or leaves this system according to traditional understanding. But what happens when atmospheric scientists examine water movement using advanced monitoring technology? The 2025 atmospheric studies reveal something that completely challenges this fundamental assumption. Sophisticated satellite observations and climate modeling show water vapor transport involves far more complex interactions than previously recognized. Water molecules actually escape from Earth's upper atmosphere into space through atmospheric processes that weren't fully understood until recently. Meanwhile, micrometeorites and space dust contribute water to our atmospheric system from extraterrestrial sources. These exchanges occur continuously, affecting Earth's long-term water balance over geological timescales. The deep Earth also participates in water cycling through subduction zones that carry water-rich minerals into the mantle. Volcanic eruptions release this water vapor back into the atmosphere through processes that connect surface water systems with a planet's interior. These discoveries show that global water distribution involves exchanges with both outer space and deep Earth systems that traditional models completely ignored. But misconceptions about planetary systems extend to underwater features that shape our ocean floors. Continental shelf variations. Ocean floors reveal underwater landscapes that challenge every assumption about what lies beneath coastal waters. Most people assume continental shelves create shallow underwater platforms that gradually slope into deeper ocean waters. This mental image shows uniform shallow areas extending from coastlines before dropping off into the abyss. Geography textbooks reinforce this perception with simplified diagrams showing consistent shelf depths around the world. But what do the latest underwater mapping technologies actually reveal about continental shelf depths? The 2025 bathymetric data shows something that completely contradicts this uniform assumption. Advanced multi-beam sonar systems and satellite-derived measurements reveal continental shelves with dramatically different characteristics across various regions. Some continental shelves plunge into incredibly deep waters within short distances from shore. Near active subduction zones, shelves drop abruptly into ocean trenches thousands of feet deep. The Pacific coast features narrow shelves that fall away rapidly, while Atlantic regions often display wider, more gradual slopes. Geological factors create these massive variations in shelf structure. Tectonic plate movements push some shelves upward while others sink dramatically. Glacial erosion carved deep channels during ice ages, creating complex underwater topography. Sediment deposits from major rivers build wider shelves in some areas, while strong ocean currents strip material away in others. Continental shelf geography turns out to be far more diverse and complex than the simple shallow platform model suggests. But these underwater variations pale in comparison to how dramatically ocean behavior changes at different locations around our planet. Global tidal variations. Tidal measurements from coastlines worldwide reveal variations so extreme they challenge everything we think we know about ocean behavior. Most people assume tidal ranges remain fairly consistent around the world. After all, the moon's gravitational pull affects our entire planet equally, so high and low tides should be similar everywhere, right? This assumption seems logical since the same celestial mechanics drive tidal forces globally. But actual tidal measurements tell a completely different story. The 2025 tidal data from monitoring stations across the globe shows variations that seem almost impossible. The Bay of Fundy in Canada experiences tidal ranges exceeding 50 feet between high and low tide. That's enough vertical change to submerge a 4-story building twice daily. Meanwhile, the Mediterranean Sea barely registers tidal changes at all, with some locations experiencing differences of less than 12 inches. These massive variations result from complex geographical factors that amplify or dampen tidal forces. Narrow bays and funnel-shaped coastlines concentrate tidal energy, creating enormous ranges. The shape of ocean basins, underwater topography, and coastal configurations all influence how tidal waves behave when they reach shore. Continental shelf width also plays a crucial role. Wide, shallow shelves allow tidal energy to build gradually, while steep underwater drop-offs dissipate tidal forces quickly. These geographical influences extend beyond ocean surfaces to affect other planetary systems in equally surprising ways. Atmospheric layer boundaries. Atmospheric structure defies the neat diagrams found in every school textbook. These educational materials show Earth's atmosphere divided into orderly layers stacked like pancakes. The troposphere at the bottom where weather happens, followed by the stratosphere with its ozone layer, then the mesosphere, thermosphere, and exosphere extending into space. These simplified diagrams create the impression that atmospheric layers maintain clear boundaries that separate them completely. But the actual atmospheric structure looks nothing like this orderly textbook image. The 2025 atmospheric research reveals something that challenges these fundamental assumptions entirely. Advanced monitoring systems show these layers don't maintain fixed boundaries at all. Instead, they blend together in complex ways that vary dramatically based on location and time of year. The tropopause, supposedly marking where the troposphere ends, sits much higher over the equator than over the polar regions. The ozone layer thickness changes seasonally and geographically, creating uneven protection from ultraviolet radiation. Mountain ranges and ocean temperatures create localized variations that completely disrupt the standard layer model. Climate change continues altering these atmospheric boundaries, shifting the tropopause height and modifying temperature profiles throughout all layers. What appears as simple atmospheric layering in textbooks represents a dynamic, constantly changing system. But atmospheric complexity isn't the only natural system that behaves far differently than scientists once predicted. Ocean current predictability. Ocean currents shape global navigation and climate predictions through patterns that seem remarkably consistent. Shipping companies plan routes based on these reliable flows, while meteorologists use current data to forecast weather patterns months in advance. The Gulf Stream carries warm water northward with clockwork precision, while the Antarctic circumpolar current circles the southern continent like a massive conveyor belt. But what happens when these supposedly stable systems start behaving erratically? The 2025 oceanographic studies reveal something alarming about current reliability. Advanced monitoring systems show major current systems developing unprecedented variability in both strength and direction. These changes occur over weeks rather than decades, completely disrupting established forecasting models. Rising sea temperatures alter the density gradients that drive these currents, while melting polar ice changes ocean salinity levels across entire basins. The Gulf Stream shows clear signs of weakening, with flow rates fluctuating unpredictably. Arctic currents shift direction without warning as ice patterns change dramatically. Climate change creates interconnected disruptions that compound current instability. Altered wind patterns modify surface currents, while deep water formation processes slow down in polar regions. Natural climate cycles like El Niño now interact with human-caused changes in ways that make accurate predictions nearly impossible. These dynamic ocean systems represent just one example of how seemingly stable geographical features actually involve far more complexity than simple models suggest. Tectonic plate boundaries. Geological textbooks present tectonic plate boundaries as clean, simple lines separating different plates across Earth's surface. These diagrams make plate boundaries appear like borders on a political map, precise divisions that clearly separate one plate from another. But what happens when geologists examine these boundaries using advanced monitoring equipment? The 2025 tectonic research reveals something that completely changes this neat picture. Modern GPS measurements, seismic monitoring systems, and detailed geological mapping show that plate boundaries aren't simple lines at all. Instead, they represent complex zones spanning hundreds of kilometers where multiple fault systems interact simultaneously. The Ring of Fire around the Pacific Ocean perfectly demonstrates this complexity. Rather than a single fault line, it consists of multiple overlapping plates, including the Pacific, Philippine, and Nazca plates, all converging through different geological processes. These boundary zones contain networks of faults, volcanic chains, and seismic activity that spread across vast areas. This complexity directly influences geological activity patterns. Convergent boundaries create mountain ranges and volcanic eruptions across wide regions rather than along narrow lines. Transform boundaries generate earthquake swarms that affect extensive areas. The distributed nature of tectonic activity makes geological hazard assessment far more complicated than simple boundary line models suggest. These same complexities affect the most basic tools we use to navigate and map our planet. Geographic coordinate systems. Latitude and longitude measurements depend on systems that constantly shift beneath our feet. Most people assume geographic coordinates represent fixed, unchanging points that remain accurate forever. After all, latitude and longitude seem like basic mathematical measurements that should stay constant. If a location sits at 40.7128 degrees north, 74.0060 degrees west, that's where it stays permanently, right? But what happens when you examine how coordinate systems actually work in practice? The 2025 datum system updates reveal something that completely challenges this assumption. Different reference systems like the World Geodetic System 1984 and the North American datum of 1983 assign slightly different coordinates to identical locations. These variations seem small but accumulate into significant positioning errors across large distances. Tectonic plate movement creates even bigger problems for coordinate accuracy. Plates shift several centimeters annually, gradually moving entire landmasses away from their recorded positions. GPS systems rely on WGS-84, which requires regular updates to account for these continental movements. Without constant recalibration, navigation systems would become increasingly inaccurate over time. Modern mapping technologies must handle these coordinate variations through sophisticated software that automatically adjusts for different datum systems and plate movements. Surveyors working on major construction projects face costly errors when coordinate systems don't match properly. Even the most fundamental tools we use to locate ourselves on Earth involve far more complexity than anyone realizes. Geography continues evolving as rapidly as the technology we use to study it. These 50 myths reveal how 2025 satellite measurements, GPS tracking, and advanced monitoring systems expose decades of outdated information that millions still believe. The facts you learned in school represent snapshots from decades past, not current reality. Continental drift continues happening right now. Ocean currents behave unpredictably. Even basic coordinates shift due to tectonic movement. These discoveries emerge constantly as measurement techniques improve and new data becomes available. These misconceptions shape how we view climate change, resource distribution, and global relationships. When geographic understanding stays frozen in time, we miss critical changes happening around us. The world keeps moving, and our knowledge must move with it.